Hi guys, welcome to my YouTube channel. My name is Dhanush R. I am studying in Sri Venkateshwara College of Engineering. Today we are going to discuss about mathematical engineering. In that my topic is pedal equations. In that differential calculus we are going to discuss today. Pedal equations of polar curves. Polar coordinates. A point in a polar coordinates is defined by two values, the radial distance r and the angle theta. The real radial distance r represents how far the point is from the origin, also known as the pole. Polar coordinates are an alternative coordinate system used to describe the positions of points in a two-dimensional plane. The angle theta represents the counterclockwise rotation from a reference direction, typical and positive x-axis. The point is denoted as r and theta, where r is non-negative real number and theta is typically measured in radians. Polar coordinates are especially useful for describing and analyzing patterns and shapes with radial symmetrical such as circle, spirals and many types of functions. Polar curves. Polar curves are a class of mathematical curves represented in polar coordinates, which consist a radial distance and angle theta. Unlike Cartesian curves, which are expressed as functions of x and y, polar curves describe the relationship between r and theta. Polar curves are commonly used to represent patterns and shapes that have radial symmetry and are naturally expressed in a polar coordinate system. Common examples of polar curves include circles r is equal to constant, cardioids r is equal to a into 1 plus cos theta, spirals r is equal to a into theta, lemniscates r into 2 is equal to a bar 2 star cos 2 theta. Polar curves often have visually appealing and geometrically interesting shapes, making them a fascinating subject of study in mathematics. And the pedal curve. The pedal curve is a mathematical concept related to polar curves, which provides insights into the relationship between polar curves and a fixed point called the pole. To create a pedal curve, we start with a given polar curve, and from each point on the curve, we drop a perpendicular line to a fixed point known as the pole. The resulting collection of the feet of these perpendicular tracks out a new curve known as the pedal curve. The pedal curve helps us to understand how points on the original polar curve relate to the pole and how their positions change when projected onto the pedal curve. This concept is not only mathematical interesting but also has practical applications in fields like physics and engineering for understanding circular and radial patterns. Properties and applications of polar curves. Pedal equation for polar curves has several interesting properties and practical applications. Firstly, we are going to learn about the properties. First one, symmetry. The pedal curve is symmetric with respect to the polar curve. This means that if the original curve exhibits certain symmetric, those symmetries are preserved in the pedal curve location of the pole. The choice of the pole's location can significantly affect the shape and characteristics of the pedal curve. Different poles locations yield different pedal curves. Special cases. Some pedal curves exhibit integrating properties such as loops, scoops, or self intersections, depending on the original curve's equation. Second one, applications. First one, mathematics. The pedal equation is valuable tool for studying polar curves and their properties, allowing mathematicians to explore relationships and pattern within curves. Physics. In physics, the concept of pedal curve is useful for understanding orbits, especially in the involving central forces. It provides insights into how an object's trajectory changes concerning a center pole engineering. The pedal equation can be applied to analyze the paths of mechanical linkages and study patterns generated by rotating machinery geometry. The pedal equation is a fundamental concept of geometric analysis, offering a way to go and investigate the shapes and transformation of polar curves. We can explain this by taking an exemplar problem. Find the pedal equation for the following curve. First problem, 2a by r is equal to 1 plus cos theta. So now we can solve it by pedal equation solution. Consider 2a by r is equal to 1 plus cos theta. We can take it as equation 1. Now we should take log on both sides. Take log on both sides. Log 2a by r is equal to log of 1 plus cos theta. Log 2a minus log r is equal to log of 1 plus cos theta. Now we should differentiate both sides with respect to theta. 0 minus 1 by r into dr by d theta is equal to 1 into minus sin theta by 1 plus cos theta. Now minus 1 by r into dr by d theta is equal to minus sin theta by 1 plus cos theta. Now minus 1 by r into dr by d theta we can take it as cot pi. Then we should substitute minus sin theta by 1 plus cos theta by the formula taking cot pi is equal to 2 into sin theta by 2 into cos theta by 2 by 2 cos square theta by 2. Cot pi is equal to, now the cos and cos get cancelled, only 2 gets cancelled, then there is only remaining tan theta by 2. Cot pi is equal to tan theta by 2. Tan pi is equal to cot of pi by 2 minus theta by 2. Then cot gets cancelled. Pi is equal to pi by 2 minus theta by 2. We know that p is equal to r into sine. This is pedal equation. P is equal to r into sine pi by 2 minus theta by 2. We can take it as equation 2. From equation 1, 1 plus cos theta is equal to 2a by r. 2 cos square theta by 2 is equal to 2 into a by r. Cos square theta by 2 is equal to a by r. From equation 2, we can substitute cos square theta by 2 in place of a by r. P square is equal to r square cos square theta by 2. P square is equal to r square dot into a by r. P square is equal to r into a. R gets cancelled. Summary. To summarize, in this presentation, we have explored the concept of pedal equation of polar curves and its significance. We began by introducing polar coordinates, a different way to represent points in a two-dimensional plane using radial distance and angle. The pedal curve, a fascinating mathematical construction, is generated by dropping perpendiculars a fixed point, the pole, to a given polar curve. We also explored the properties and practical applications of the pedal equation, from analyzing planetary orbits and mechanical linkages to design, robotics, and the even artistic creations. Understanding the pedal equation provides valuable insights into the geometry and behavior of the polar curves in various fields. Thank you. Thank you for listening this class, and I hope it is helpful for everyone, and thank you.